Good morning, everyone. I'm Diana, and I'm the Marketing Communications Manager at Norsat. On behalf of the company, I would like to thank you for joining us today in our SATCOM 101 webinar, which will serve as a great introduction to the key principles of satellite communications. If you're new to the industry, such as myself, this presentation will definitely help deepen your knowledge on SATCOM and its products. I'm delighted to introduce our presenter today, Rodrigo Aguilar, Customer Service Engineer at Norsat. With over 15 years of experience on satellite communications, Rodrigo has participated in multiple projects deploying and installing satellite terminals and antennas for their use in fields such as broadcast, military, and emergency services. He's responsible for Norsat's customer service team providing technical support, training, and on-site implementation. He has a Bachelor's of Science degree in Electronics and Communications Engineering. We'll begin with the presentation by Rodrigo, after which we'll open the floor up for questions and answers. Please use the question box in your control panel to submit your questions throughout the webinar, and we'll address them at the end. Just a few housekeeping items before we start. If you're currently not subscribed to a newsletter, please do so to stay up to date with our latest news, webinars, product launches, and company news. You can subscribe by filling out the subscription form on our website, www.norsat.com. We also welcome your feedback on our webinars, as we're always looking to improve them and cover new topics that would interest you. So please complete our short survey, which will be sent out to you after the webinar. Now, without further ado, Rodrigo Aguilar.
Good morning, and thank you for joining us today in our Satellite Communications 101 webinar, where we will cover the fundamentals of satellite communications and SATCOM systems. My name is Rodrigo Aguilar, and I will be glad to provide you this session today. The topics we will be covering today are an introduction to satellite communications, where we will explain what satellite communications are and their advantages and disadvantages. Then, we will move on to the fundamental mechanics of how satellite communications work. Later on, we will explain the different frequencies and bands satellite communications use. After that, we will talk about earth stations and the multiple components used on those type of communications. And last, but not least, we will cover some of the key considerations to look out for when selecting your satellite terminals and components. Let's get started. Let's begin by defining what is a satellite. A satellite is an object in space that circles around a larger object. An artificial satellite is an object that has been intentionally placed into orbit for communication purposes. Their main function is to retransmit any signal that they receive back to Earth, allowing long-distance communications. The satellite will only retransmit signals without modifying the original message. This means that the satellite will not provide any additional security. The information security has to come from the signal source. The most common types of applications for satellite communications include voice and telephone, television and radio broadcast, data for network and internet access, navigation and global positioning systems, scientific research, and meteorology for both commercial and military industries. There are multiple classifications for satellites. The most common classification is by the orbit that they operate. An orbit is the path of a celestial body or an artificial satellite that circles around another body. The basic orbit types are classified depending on their altitude. The closest orbit to Earth is the low Earth orbit. Satellites in this orbit travel relatively fast to remain in orbit and circle around Earth about every 90 minutes. Examples of objects in this orbit are the Hubble telescope and the International Space Station. A little bit further one is the medium Earth orbit. They travel slower, close to 12 hours per revolution, around Earth. Navigation systems like GPS, GLONASS, and Galileo satellite systems operate in this orbit. Geosynchronous and geostationary orbits have an altitude that synchronizes with the Earth's rotation. The only difference is that geostationary remains on the same plane as the equator, while geosynchronous can have some inclination where the object appears on the same position in the sky every 24 hours. Satellites on a geostationary orbit are the most commonly used, and what this webinar will be mainly focused. The furthest orbit is the high Earth orbit, which are usually dedicated for scientific research applications. Some advantages of using satellite communications is that the cost is independent of the distance between Earth stations. It does not really matter how far away the two Earth stations are, the cost will not increase due to its distance. This flexibility makes satellite communications a viable solution for some applications like oil and mining industries. Also, satellite communications can help reduce the cost compared to building long and complex landlines with other technologies like cable and fiber for remote locations. Additionally, some short-term applications like events or temporary installations can involve a big investment that cannot be cost-effective for the short amount of time they last. News and sport events are a typical example of short-term installations that use this advantage of satellite communications. Mobility is another great advantage. Portable terminals offer great flexibility to deploy and move an Earth station very quick. Satcom on the move also offer a reliable link for ground, maritime, and airborne vehicles that are constantly moving. Even more, satellite communications are highly adaptable and versatile. Nowadays, switching, changing, or adding services might involve a very small investment. On the other hand, some of the major disadvantages of this technology is the high cost of specialized equipment that satellite communications use. Especially for short distances, other types of technology like cable, terrestrial, or fiber communications will have a lower cost. Another disadvantage is the limited frequency spectrum that satellite communications can provide, and that once they reach full capacity, they cannot be upscaled. Satellite communications are also susceptible to electromagnetic interference, or EMI. Power lines that generate powerful electromagnetic fields or other terrestrial communications in the same frequency range can significantly affect satellite communications. One example that is discussed nowadays is 5G, where the frequency range overlaps with satellite C-band range. Also, satellite communications are highly susceptible to some environmental conditions. Microwaves can be absorbed by moisture, rain, or snow, reducing the performance of the link. Solar outages are another phenomenon where the radiation of the sun interferes with the signals used in satellite communications. Fortunately, they only occur twice a year, around the spring and fall equinox. Now, let's talk about how satellite communications work. The concept is to create a channel between a source and a recipient. These points are called Earth stations or ground stations. The source will transmit a signal that the satellite will rebroadcast back to Earth for the recipient to receive that signal. Some applications only use a one-way path where a single source will send to one or more recipients. This technique can be used for broadcast and multicast communications. An example is satellite television, where the TV station will send a TV channel over the satellite with multiple subscribers receiving it. Also, There are some applications that use two-way communication, where both earth stations transmit a signal to each other on a point-to-point communication. Network data is a great example where both earth stations transfer information to each other, creating a connection between the two networks. This is normally used for internet and internet connectivity on some locations where other technologies are not easily accessible. The basic function of an earth station is to transmit and receive signals to a satellite. The signal that is transmitted to a satellite is called uplink, and the signal received by an earth station is called downlink. Due to atmospheric conditions, such as rain and snow, the signal can be weakened. To compensate for this loss, the earth station must amplify the signal before it is transmitted and once it is received. Additionally, to maximize the power transmitted to the satellite, the energy of the signal is focused on a narrow beam. To achieve this highly directional beam, satellites and earth stations use antennas with parabolic geometry. The point of source, or more specific, the feed horn, is placed at the focus of the parabola to direct radio waves in one particular direction. The radio waves bounce in the reflector, which is made of a reflective material. Normally, it's made of metal or a metal layer with other components to make it lighter. The antenna provides a gain that is proportional to the size of the reflector and the wavelength of the signal used. The bigger the antenna, or the higher the frequency, the greater the gain. There are different types of antennas depending on the shape of the reflector, or dish, and the position of the feed. The most common ones are front feed and offset feed. A satellite consists of multiple subsystems that allow it to operate and provide services throughout its expected lifetime. One of the most important ones is the communication subsystem that consists of segments of bandwidth that are called transponders. Their primary function is to receive, amplify, filter, and rebroadcast a signal. There's also an additional conversion in a satellite that avoids interference between uplink and downlink signals. Now, let's talk about how the information from the earth stations is transported through space. This is achieved through an electromagnetic wave. This consists of a synchronized oscillation of electric and magnetic fields. They are normally measured by its frequency or wavelength. These artificially generated radio waves are used on many types of applications, such as fixed and mobile radio, broadcast, radar, navigation systems, and many more. Polarization is the property of an electromagnetic radiation in which the direction and magnitude of a vibrating electric field is propagated in a specific way. In satellite communications are used two types: linear polarization with horizontal and vertical components, and circular polarization with left-hand and right-hand components. This property allows to use the same frequency twice in the same satellite without interfering each other. This is called reuse of frequencies and allows to double the bandwidth capacity of the satellite. Depending on the frequency that the earth station operates, the signal can be categorized in bands. The ones used in satellite communications are C-band, between 4 and 8 GHz, is primarily used for voice and data communications. Because of its weaker power, it requires a larger antenna, usually above 1.8 meters. However, due to the lower frequency range, it performs better under adverse weather conditions on the ground. X-band, between 8 and 12 GHz, is used mainly for military communications and wideband global SATCOM systems. With relatively few satellites in orbit in this band, there is a wider separation between adjacent satellites, making it ideal for SATCOM on-the-move applications. This band is less susceptible to rain fade than the Ku band due to the lower frequency range, resulting in a higher performance level under adverse weather conditions. Ku band, 10 to 18 GHz, is typically used for consumer direct-to-home access, distant learning applications, retail, and enterprise connectivity. The antenna sizes, ranging between 0.9 meters and 1.8 meters, are much smaller than C-band because a higher frequency means the higher gain can be achieved with a smaller antenna size. Networks in this band are more susceptible to snow and rain fade, especially in tropical areas. Ka band, between 26 and 40 GHz, is primarily used for two-way consumer broadband and military networks. Ka band dishes can be much smaller and typically range between 60 centimeters and 1.2 meters. Transmission power is much greater compared to the C, X, or Ku band beams. Due to the higher frequencies of this band, it can be more vulnerable to signal quality problems caused by snow and rain fade. Now, let's talk about earth stations and its components. There are different types of earth stations. Fixed earth stations are installed on a permanent or a temporary location. Portable terminals, or flyaways, are compact transportable earth stations that can be packed, transported, and deployed easily. Satellite communications on the move are normally referred to a vehicle that is equipped with a satellite antenna that can establish and maintain a satellite communication link while the vehicle is moving. This vehicle could be a ground, maritime, or airborne. The most used components in satellite communications are modulators, demodulators, and modems that transforms digital information into signals that can be transmitted through space. They use a generic band, L-band, that allows them to be compatible with any satellite band on a particular application. Another component are amplifiers, such as block-up converters, or BUCs, that will convert the frequency from the generic band to a specific satellite band and amplify it. A low noise block, or LNB, will do the opposite, converting a downlink frequency in a specific band to a generic band, or L-band, that the modulators and modems work. Filters are important components that will allow to reduce interference from undesired signals as well as providing the polarization of an earth station. Another component is the reflector that can provide better performance or portability depending on the material, construction, and size in a particular application. Earth stations normally consist of an outdoor unit, an indoor unit, and an interfacility link. An outdoor unit, or ODU, are components or subsystems that are installed in an outdoor location. These normally are designed or enclosed to be weather resistant. An indoor unit, or IDU, are the components or subsystems of an earth station installed in an indoor location or weatherproof shelter. The interfacility link, or IFL, is the cable system that connects the outdoor unit with the indoor unit. The components normally found in an outdoor unit are the reflector that is oriented to the satellite, the antenna base that provides support to the rest of the outdoor components, the feed horn, which is the gate where signals come in and out of the terminal, filters that reduce interference and filter signals with specific polarization, LNBs, and BUCs. The outdoor unit can be motorized to automate the motion of the antenna for satellite acquisition and tracking purposes. This means the terminal can point and keep the antenna oriented to a satellite automatically. The control of a motorized antenna is done by the Antenna Control Unit, or ACU, normally located in the indoor unit. Also, the outdoor unit can be used without motors to reduce size and weight, where the operator needs to move the antenna mechanics by hand. The orientation of an antenna is measured in 3 angles. Elevation, reference to the horizontal plane. Polarization, reference either in the horizontal plane in linear polarization or the direction of the signal spin in circular polarization. And azimuth, reference to the geographical north, known as true azimuth, or to the magnetic north, known as magnetic azimuth. Motorized antennas can have 3 motors to control the movement of the antenna in azimuth, elevation, and polarization. In manual antennas, the operator must do the adjustments on these angles by hand. Some systems may have software to assist with the calculation of the looking angles to a specific satellite, or the operator has to use handheld instruments like compass and inclinometer to know the azimuth, elevation, and polarization position of the antenna. As mentioned, the indoor unit contains equipment that are indoors or in a shelter that are not designed to be weatherproof. These are normally modulators, demodulators, satellite receivers, modems, or tracking devices. These devices are normally rack-mounted and installed inside a building or in a temperature-controlled room. In the case of portable antennas, this indoor unit can be a portable rack that can be transported with the antenna, but still requires a shelter or a weatherproof location nearby the antenna when it is in operation. Digital audio-video encoders and network components, like laptops or network routers, are normally connected to a modulator or a modem, typically through an IP connection. The IFL is the cable system or group of cables that connects between the outdoor unit with the indoor unit. They normally transport signals for the uplink or from the downlink, monitor and control signals to remotely control the outdoor equipment and monitor status in case of failures. IFLs can also include a power line that can energize any outdoor equipment if requires an external power source. This diagram illustrates the components that process and converts the information throughout the full path in a communication link. The information is converted by a modulator to a generic band, in particular L-band, before it is transmitted to the satellite. Then, the signal is converted to a higher frequency and amplified in one of the satellite bands by the buck, for example, from L-band to Ku-band. The output signal goes through some filters to reduce interference and add the polarization, and then the antenna will send the signal to the satellite. Once the signal is received by the Earth station, it is processed the same way, but in reverse order. The signal is filtered, amplified, and the frequency is converted to a generic band, in this case L-band, by a low noise block, or LNB, and finally converted by a demodulator or satellite receiver to recover the original information. There are other components in the market known as up converters and solid-state power amplifiers, abbreviated SSPA, that can do the 2 main functions of the buck, the frequency conversion and amplification, separately. Depending on your application, it might require using them instead of a buck. Another similar case is the LNB, where the amplification and frequency conversion can be done by a low noise amplifier and a block down converter, respectively. Modems is a combination of a modulator and a demodulator within the same device. In order to determine the adequate equipment for a specific link, it is required a link budget. A link budget is a summary of all the power, gains, and losses that a communication signal experiences in a telecommunications system. This summary is used to ensure that the information received by an earth station has an adequate level to recover the information properly. Gains are obtained from components such as amplifiers and antennas, and losses are obtained from cabling, filters, and atmospheric propagation. A link budget can help to determine the amount of amplification, bandwidth, and parameters required for a specific application. If we take a look to the graph shown, it starts on the left-hand side with the modem output level. Then the signal has a loss through the IFL, depending on the distance and the quality of the cable. After that, it gets amplified by a buck in the outdoor unit. The reflector will provide an additional gain, depending on the size and the band used. The signal has a loss traveling through the atmosphere. The satellite will provide a gain to the signal and rebroadcast it back to Earth. The signal will have an additional loss on the downlink path. The antenna and the LMB in the outdoor unit will provide a gain to the received signal. The IFL will have an additional loss, resulting on the final signal level that the satellite receiver, the modulator, or modem will get. Things to consider is the sensitivity or minimum signal level that these devices can operate, and add a safety margin to ensure proper reception in case of an additional unforeseen losses. Finally, let's talk about some basic considerations that can help you selecting the right product. When buying terminals, it is important to keep in mind the frequency band and range that the terminal will be operating. Different countries and regions use different frequency ranges. The type of application, whether if it's going to be fixed or mobile, and any special requirements like output power or reflector size. Also, some operations will require to find satellites automatically with motorized mechanics, instead of the operator manually point the antenna to the satellite. Another important thing to consider is the size of the terminal and how portable it is. Flyaways are small and portable that are suitable for emergency and short-term events. Fixed antennas normally are larger terminals which provide better performance but require a permanent installation. When buying box, it is important to consider the frequency band and range of the system is going to be installed. Also, the gain and output power according to the calculations in the link budget. Some applications will have additional requirements such as power consumption or form factor, especially if they will be installed in vehicles or must comply with a specific certification. For the LMBs, the frequency band and range of the system is important. Also, there are other parameters like gain, frequency stability, phase noise, and if the reference they use to make the frequency conversion is external or internal. This concludes the presentation of our webinar. Now, we will open the panel for questions.
Rod, so thank you very much for that enlightening presentation. Now we're going to open the floor up for Q&A. So I welcome everyone to submit their questions through the question control panel to your right. So the first question we have is, on slide 14 in your diagram, you have a photo of OMT. Can you please explain what that is and what it does? Rod, I think you have to unmute yourself. You're on mute.
Okay. Thank you, Diana. I'll go back. Slide 14, it mentions the OMT. I think it's slide 13. Okay. An OMT is it stands for orthomode transducer. It basically provides the polarization of the system. It's a filter that it's attached to the feed horn, and this basically splits the polarizations that the system is using. In this case, the photo that we have is for linear polarization, where it splits the horizontal and vertical polarizations. One port is going to be one polarization, and the other port is the other one. The circle one that is facing to the front is the one that is attached to the feed horn.
Okay. How many years does it take for an LMB to be considered aged? How often should you be changing the LMB, for example, after how many years?
That depends from manufacturer to manufacturer, depending on what type of electronics and the technology used. If the electronics are more refined, the expected mean time between failure is going to be much longer. And also depending on the environmental conditions and the stress, the electrical stress that the unit is normally used. Normally, manufacturers can provide an expected lifetime and provides a warranty based on that, but if with proper maintenance and with the proper care, they can last for many, many years.
The next question is, how does the reflector look like?
The reflector, well, most of the antennas, the reflector is just the round portion that it is in an antenna, and it's basically it's a reflective electromagnetic surface that will, all the electromagnetic waves are going to be bounced against that surface. It's most of the time they are circular, because the radiation is distributed evenly, but also it can have multiple or different shapes depending on the pattern of how the electromagnetic waves are provided by the feed or received, depending on the wavelength that is used.
Is there one common L-band?
L-band is commonly a range between around 1 and 2 gigahertz, and common devices like modems and receivers, they use this band regardless of which transmission band is going to be used in the system. This provides some flexibility when using modems. They don't have to be specialized for KU band or a KA band. They can use this generic band, and there are devices like block-up converters, bucks, that will provide the up conversion to a specific satellite band.
Are there multiple modem protocols? And if so, is there a modern technical reason for this? For example, could there just be one?
Depending on, there are multiple standards that follows satellite communications there. Depending on which one is used, we have the DBB, we have the new tech, but these ones they have their own standard, and depending, they have more advantages and disadvantages on using them. Obviously, the intent is to have more throughput with less bandwidth and less power, but definitely different standards can provide different advantages depending on the application.
I understand that NORSAT produces a filter to avoid interference from future terrestrial 5G. Please explain how it works.
We actually had recently a webinar regarding 5G, and this definitely explains a little bit more in depth. It's a completely different topic, but the main intention of having this product is to have the LMB combined with a bandpass filter that can help reduce the interference from 5G interference. The advantage is to have a combined solution in one product.
If you have an old KU band system, what are the components to change to move to a KA system?
Normally, the reflector is probably nothing. It's not going to change. Both bands can work with the same reflector, as especially if you're going on a higher frequency. The requirements for a larger reflector is it's not a problem. It's actually Ka band will require a smaller dish, or if you have already a reflector, it's going to have a much higher gain. Probably the bucks and the LMBs are going to be changed to one for that specific band, and the filters and the waveguides associated with it.
Can a device that handles KU band also be used for KA?
Similar to the previous question. Yes, the reflector and anything attached to the up converter and down converter, the modems, certainly can still be used. It's mostly the LMB, the buck, and the filters associated.
I saw the term SSPA. Can you comment on what the acronym means?
SSPA is a type of amplifier. It stands for solid state power amplifier, and within amplifiers for these high frequencies, they normally there are different types like Klystron tubes or TWTA, but SSPA is a particular one that are based on transistors, and there's an advantage that these ones can be very, very compact, and also the power consumption could be much less than the other types of technology.
Do you need to use a noise rejection filter for a circular KA system?
Depending if you have interference, but certainly if you make your calculation on a link budget and you make a study, if you have any kind of interference or something external that can affect, certainly filters can help to reduce undesired signal.
In what cases would you need a rejection filter?
there are some times with the terrestrial communications will have much higher power than the signals that are received on satellite communications, and those ones will basically cover the signals, and also this type of communications can produce some harmonics or spurious out of the band that can interfere with the bands on satellite communications. Filters, rejection filters, will help to reduce that. Also, within the same system, the power of the buck is much higher than the signal received because it's using the same feed horn. They might require a transmission reject filter to reduce the amount of power that is leaked between the transmit port and the receive port.
How do you know RX sensitivity?
The manufacturer of the modems or the receiver will provide you the minimum requirement in order for recover the information. Looking by the specifications, they normally come with a minimum, and depending on the signal coding and all the parameters of the signal that it's transmitted, there's a correlation between sensitivity and the all these characteristics of the signal that will help you to decide which is the minimum margin that you can have on your path.
I understand how the antenna is positioned for AZ and EL. Can you explain in general how the antenna is positioned for polarization?
There are tools online that can help you get the calculations. It's all triangles, azimuth, elevation, and polarization are a mathematical formula, and I think, as mentioned, the polarization is reference to the horizontal plane. Of course, the satellite, because the geographical position of the terminals and the orbital position of the satellites are not completely aligned, that's where you have to tilt your polarization in order to align to the horizontal plane of that satellite in that particular orbital position.
For a frequency band that had been selected, how can we determine the diameter of the antenna?
Sorry, can you repeat that one again?
For a frequency band that has been selected, how can we determine the diameter of the antenna?
The antennas, the manufacturer of the antenna will provide you the gain of the antenna for a particular frequency.
My question is on slide 11, the satellite frequencies and bands. Can these be utilized at the same time on the same IDU and ODU?
There are antennas that can have feeds with multiple bands. Yes, they can exist, and but if there's a limitation because it takes some space, normally is recommended that, or you will see that antennas will have one band in specific, and can be used to transmit, receive, or receive both polarizations at the same time.
Here's another question relating to 5G, and for all of you who have questions about 5G, I highly urge you to check out our 5G webinar that our Chief Scientist, Mike Schefter, delivered a couple weeks ago, and it's available on our website. This question is, with 5G coming soon to North America, can you talk about the 5G filter that will be needed to be able to still receive signals from C-band? And also, do you anticipate a lot of current C-band signals to move to KU band, and also moving more moving to HEVC and PEG5 H.265?
Okay, I think this is a little bit mixed. Definitely, well, for 5G, which operates in 3.5 gigahertz, and it's gonna start interfering more earth stations using C-band. Yes, because it's only a portion of the C-band, and because of the power, it can start to interfere with the rest of the C-band portion. Bandpass filter can reduce any excessive power that is leaking into the satellite antenna. The rest, I think it's mentioned something about H265. This is not technically related to satellite communications. It's more coding, video encoding. But certainly that is just data, and as long as it's digital, a modem can transmit it on any band for satellite communication.
What are some of the factors that determine LO oscillator stability, and does LO stability differentiate with the LNB prices?
Yes, the LO stability is basically how much range is the down conversion, and how stable is the down conversion between the downlink frequency and the L band. The tighter it is, for the more refined electronics that that is required to have a better down conversion. Of course, that is associated with the price of the LNB. Applications with very, very small bandwidth will require a much higher LO stability to lock to that signal. The larger the bandwidth, they can allow a little bit more range to oscillate, or doesn't require to have that tight LO stability in order to lock to that signal.
Is the X-band antenna larger than the KU band antenna?
A little bit back on this slide. It not necessarily is that you will require a large antenna, but you will definitely have more gain in KU band than X band. Or on the other way around, if you want the same gain, yes, you can achieve it with a smaller antenna. Okay.
How can we eliminate or reduce weather interference in KU band?
Well, you can't avoid weather effects on signals, but certainly you can run your leaking budget exercise and consider best and worst case scenario, and still cover a margin on those scenarios to make sure that you have a good and reliable link.
Next question is, what products does NorSat offer?
We invite you to go to our website. We have for satellite terminals, we have LNBs, box filters. Certainly, there's a large catalog in our website, and with many different types of specifications, characteristics, and I'm pretty sure that one of our sales representatives will be more than glad to assist you.
How do you differentiate on the use between an SSPA and TWTA?
TWTAs are can be rack mounted, but they still use some sort of backing tube. They tend to be much bigger. SSPAs, as I mentioned, they use electronic components and transistors that will allow it to be much more compact for the same output power.
For NorSat KA buck, what is the max power, and can we offer a customized product with higher gain or remove buck stage to be waveguide KA input?
Yes, we do customization on products. If I'm not mistaken, our catalog 50 watts on KA is the one that we offer. But if you require something more concrete and specific, please contact any of our representatives. We can have a discussion on specific requirements and get a product for you.
You mentioned C-band. What about extended C-band?
Even within C-band and or any other band, there's a range, but not all of the range is covered entirely for all transmission and all reception. Normally the transmission portion is on the higher end of each band, and the receive portion is on the lower end of each band. C-band has standard, extended, and super extended receive range, depending on the region. A lot of countries and regions, they have different regulations that will have different ranges, and that's why we have a large variety of LMBs, because depending on what is the frequency specific region or frequency range on that region is the one that is required on that specific case.
This question is related to career development. What's the career development path like for a field engineer in the SATCOM industry? Do you have any recommendations for courses? This person knows about GVF, but is there anything else?
Let me take a look and see what else, what kind of information I can provide. Yeah, I'll contact this person later.
Can two bucks be combined to achieve double power or redundancy?
Yes, actually, those are two different scenarios. Bucks are combined in a redundancy system to as a backup to reduce the service interruption between in case of failure. It can be that the backup is it's actually transmitting to a dummy load or it's just on standby. But then the output is not combined. The output, one of them is going to go to a dummy load that is going to dissipate the energy. Once it's switched, then the backup goes to the antenna. The failed one or the switch one is going to go to the dummy load. There are instances where you can combine bucks, but you will require a special arrangement because if they're not properly synchronized, some of the energy is going to be dissipated, and the waves are not completely aligned. There's going to be an inefficiency and a lot of problems of signal distortion.
And the next question is about the compatibility of 5G LNB with a SealTel VSAT system. And are 5G LNB universal or varies with antenna manufacturer or varies with KU and KE band?
I'm not particularly familiar with this application. I might need to take a little bit, spend a little bit of time just to take a look on this particular product and to understand what is the specific information on, or characteristics of this system.
What is the minimum size of a KA buck?
The minimum, well, I'm not entirely sure. We can be a couple of watts, but if you have any questions, we have our catalog in our website.
You mentioned that satellite ground terminals can be auto-pointing or motorized. Why would someone pick one over the other?
The most common ones are manually acquired because they are very light and simple to use. However, learning how to point to a satellite might require some learning curve and not necessarily all of the, it requires some experience in order to get it right and fast. Of course, auto acquisition systems, then they have everything automated. There are some instances where even getting your personnel trained to point to a satellite might require some time, and we have some customers that they rotate personnel very quick. By the time you train the person, then you have to train the next one, and that's where it's more convenient. Out-acquired systems where the training on people is basically minimum.
Why do maritime terminals on ships have a big ball over them?
That's a cover, and it's called a radom. It's basically just to protect the antenna and the electronics and the sensors that it has. That cover, or the radom, is basically made out of a material that is not going to affect signals coming in and out. It might have a minimum loss, but it's basically just to protect it from the weather, especially because it's going to be at sea. And there's a lot of water, and the temperature can get very low.
How do I decide what power or size buck I would need on my satellite terminal?
It's very good to run a link budget exercise to know, and that will help to determine your requirements for bandwidth and the data transfer that you require, which satellite you're going to use with gains, and all that will help you to determine how much output power you will require to establish a link, depending on the geographical position of the source and the receiving earth station.
Okay, I think we have time for one more question. What is the difference between a buck and an SSPA?
I think I mentioned that. This diagram helps illustrate a little bit better. So the buck does two things. It makes an op conversion and then does the amplification. That's basically what we call a buck. The SSPA is a device that only does the amplification. But the input, it has to be in the band that it operates.
Okay, well, we're perfect on time, and I just want to thank Rod for giving us this great presentation, and I hope this helped all of you to deepen your knowledge on SATCOM and the products that we offer. A copy of this recording will be sent out to you after this webinar ends, so if you want to listen to it again or share with your colleagues, please feel free to do so. Also, we'll send out a short survey. We want to get your feedback on how we can improve our webinar, and if there are other topics that you would like us to cover in the future, please do let us know. And if you have any questions, please reach out to us, and everyone, I hope you have a great day. Thanks, everyone.